Hello, welcome to the fuzzing workshop. So fuzzing is a technique for randomly testing a program, and we will discover how to use fuzzing to test a simple Node.js program that we have. And we also talk about different approaches related to fuzzing and eventually its close relationship to mutation testing. So before you get started, you can clone this or import this notebook and run the dependencies for the code that we'll have. So I'm going to roughly break up fuzzing into two different categories. So one category is basically referred to as black box fuzzing, and the other kind is called white box fuzzing. And the main idea is with black box fuzzing, you're really just using pure randomness. You're not taking into account the actual structure of the code, and you're really just trying your best to generate interesting inputs that might make a program fail or reveal a security vulnerability. So given that white box testing involves much more sophisticated analysis of the program, we will obviously be focusing on a black box fuzzing technique in this workshop. But still, there are two different types of black box fuzzing techniques, and we're going to narrow down on one of them. But just so that you know what this is about, the first approach is called generative fuzzing. And the main idea there is that you are generating the whole input yourself. You're responsible for randomly creating that input. And you're typically guided by the grammar or domain knowledge of the input. So for example, if you knew, if your goal was to generate random images that you could send into a program, and you could, like the layout of how the headers are and, all the picture information is, you could just generate random bytes for that picture and then use that as input to a program to see whether it causes something to crash, or you can, cause something like a array out of bounds error, etc. So the problem with generative techniques is that requires a little bit more effort in terms of building up basically how you generate that technique. It's not going to be kind of the easy, dumb thing you can do. And so this is where this other approach comes in, which is mutation-based fuzzing. And the idea is that you're given a set of seed inputs, and these inputs are basically like templates or captured or just kind of captured and replayed from you actually using the program. So either way, you get these files, and then the idea is that you start to randomly modify them so that you could play with different variations of that file and then try to test it. And what's useful about this is that because you have this existing file that's already made or existing input, then you don't have to really model any of the domain or the grammar and the structure of it. You could just take advantage of some human or some automated process captured that. And then your goal is then simply to just see if you can mess it up as much as possible. So a really simple example of this is, imagine you had a 200-page Word document with just all sorts of figures and tables and fonts and basically everything you can imagine in terms of using Word. And you started to randomly change the file itself and attempt to open it in Word. And then you just repeated this process millions of times until you found one version of that document that caused Word to crash when it attempted to open it, right? And that's essentially what you're trying to do with fuzzing, is you're just trying to, with blindly explore a space until you find something that causes a problem, right? And so we're going to do something very similar to this idea, except we're going to be working with Markdown. So for this workshop, what we'll be doing is we'll be testing a tool called Markdown with a Q. And what Markdown does is it takes a Markdown file and it generates an HTML rendering of that survey, of that file, which is essentially representing a survey. And what you'll see is something like this, where you have a couple of you just have Markdown information like this, and it gets rendered into a survey that you can actually take. And this is actually what's in use at Checkbox.io. So if you haven't seen that before, then it would look something like this, of where given this Markdown, this is a survey that you can create, right, and deploy. And so that's the main idea of Checkbox.io is you have like a simple Markdown way of creating surveys and administrating them, etc. All right. So because there's a lot of moving parts here in this workshop, there is code that's provided for you. And for the most part, you can run everything you need to from this notebook, but you may want to also open this locally in code just so that you could see all the other things that are here. So for example, this is this folder that I have open, and there's all these other files that you could also refer to. All right, but let's look at what the most basic thing that we're starting with. So if we look at what the index.js is doing, which is the same as this one here, you'll basically see that it is loading up this fuzzing function, and it's loading up Markdown, which is going to be the code that we're testing. And it's loading up 2 Markdown files. And it's really all the code is right here, the most important part, where it's calling the empty fuzz function with a given number of iterations to try. So 1,000 is the default. Then a list of seed inputs to be mutating, and a function that is provided that will be tested. So essentially what's going to happen is this function here, where it's calling Markdown on a Markdown file. So it's just rendering this into HTML. So this is the main translation step of the code. And it's just checking to see, if I run this thousands of times and mutate it, is this going to crash or not, right? So that's the main idea of what all this code is doing. And so if we just out of the box try to run this, then you will see it's basically saying it's running the fuzzing process with 100 or 1,000 randomly generated inputs. Then it will finish that run and say that there were 1,000 executions of that function where they all passed. There were no exceptions thrown, no faults discovered, right? So that's by default what happens. And the reason why is because the mutation step is actually just returning the seed input. It's not changing it at all. And one of the things that you're going to be doing is to actually apply the mutations. So let's break down what the actual mutate function looks like. So at a high level, what it will do is it's going to run this empty fuzz function 1,000 times, and it will each time pick one of the seeds, which is just kind of toggling between that, the first one or the second one. And it just goes back and forth each iteration, picking one of them. And then it runs the mutate string function on that file, and then passes it to our test function, which, if you recall, is basically this, which is just calling Markdown render, right? So it's calling that on the mutated strings. And then what it's doing is it's checking to see if the function will crash or not, right? So if there's an exception raised when that function is called, then it's going to basically save that input and stack trace and consider that a failed run. Otherwise, if it runs successfully without having any problems, it calls that a pass test. So this gets into kind of a more theoretical part of testing, which is this idea of a test oracle. So when you test something, you need to know, you need someone to tell you, is this a good or bad test, right? And so, or execution. And when someone creates a unit test by hand and they provide assertions, those assertions are provided by a human as the test oracle of saying that this is good or bad. The problem when you use an automated technique, you don't really have the ability to automatically know what is good or bad behavior. And so a common practice is to use something that you never want, which is a program crashing and exiting, as your oracle, right? So an exception being raised is a classic test oracle that we could use to say that, was this unexpected behavior, right? It could be that we pass in something and the program is failing in a way that we don't want it to be, but we just don't, that's not visible. And so that you would need other types of testing to discover that. But fuzzing is going to be good for finding things like it crashing on input. Okay, so this is going to be the bulk of the workshop that you will be doing on your own, but I'll walk you through a couple of these steps. So what we're going to be doing is we're going to change this kind of mutator string function to actually change that string in weird and random ways and see if we can cause that to cause problems, right? So let me go ahead and skip down below, and you can see this function here. So if you edit this and run it, then you could rerun the generation step. Let me just do something really silly just so that you could get a sense of what's going on. So what I'm going to do is I'm just going to return an empty string as my mutation. And then what would you expect to happen? All right. Well, now you see this is doing something a little bit different. So now it says that it's finished those 1,000 runs, but now it's gotten 1,000 exceptions and 1 fault. And this is what this fault looks like. So essentially it's saying, here is the exception message, and here was the input file that caused that to throw this. And then here's the stack trace of where you could see this was happening in the JSON5 module. So it was trying to parse a string, and it did not receive an expected JSON object, and then it crashed. So this is not good for sure. But sort of the problem that we're running to already is that we've discovered a bug, but we ran this 1,000 times and we basically found the same one over and over again, right? And so that's not good. And so one of the problems with, so it's good that we found a bug, and it's fascinating that we could do this automatically without any knowledge about the program. But what we're going to want to do is we're going to want to kind of more gracefully explore the space by applying random mutations, but only doing it some of the time. So that way we can kind of try little tweaks to the code or to the input and not be so aggressive. And so that's why we're going to be doing some of these other steps. So for example, one of the steps will involve, with a 25% chance, removing a random set of characters. So it's like going in to, let's look at one of these test inputs, this one. And if what happens if I just randomly delete that and run it, right? So it's, we're, some of it, right? So it's going to, by a random amount and in a random place in the file, randomly delete that file, the inputs. Likewise, with a 25% chance, insert random characters into the file, right? So insert a random string into this file. So it's just like if I started typing something, right? This one, with a 50% chance, replace a single quote character with a random integer. So in here, this is where we're starting to get a little bit more intelligent about the things that we're replacing. So if I see a quoted string like this, what happens if I just replace that with a number? Is something going to happen or not? And finally, with a 25% chance, repeat steps 1 and 2. So this is not so complicated. Like you could actually do a lot of this in a couple lines of code, but the real trick is going to be kind of thinking of the mechanics of this. So I've given you some hints on how to use this. So one of the main ones that you're going to be using is this array slice function. So if you look at this, the way that Splice works is you give it a starting position and then a number that says how many to delete, and then an optional amount of items to insert. So Splice is really interesting because you could use it to both delete from an array or to add to an array. And I can actually give you just some demos of this in a console. So let's go to a REPL. All right, and so I'm just going to be a node. And if I say a equals 1, 2, 3, 4, 5, 6, and if I say a splice position 2 items, then it's going to return what it deleted, but a itself will have the contents that remains, right? And similarly, if I do a that splice 2, 0, and then give it 3, 4, I think this is the right syntax, then it's inserted that back in. And what I've used here is called the spread operator, which is just a useful way to append something into a list. But using kind of this as a guidance, you can imagine just changing these numbers to be random and to wreak havoc with this. And so just to know how to get, I don't have this loaded, but so you see this function here, this is a random utility, and it has a couple utility functions that will be really useful. So this dot bool, where you give it a fraction, will essentially translate into with X probability, with 25% probability, execute as true or evaluate to true. And similarly, there are other functions like, where is it? Mutator random integer with a start range and an end range, and it will generate a random number from 0 to that number. So if you gave it 0 to 100, it will randomly generate something between 0 and 100, each time something a little bit different. Similarly, if you wanted to generate a random string of a length, then you could use the dot string operator with a number, and it'll give you a random string of random elements of length 10. And one last one that will be useful to know is when you replace the string quotes with a random integer, I would suggest actually doing this at the string on the top of the function, and then just using a regex to match it and replace it with the random number. So that's kind of all the moving parts that you need, and it might take a little bit while to do it. But what I'm going to do is I'm going to pause, and I'm going to implement that, and then I'm going to show you the results. But I want you to do the same thing on your own. So let's do this. All right, so I'm done coding up my thing, and I'm going to run this now to see what the results are. Okay, so it looks like I got some things to kind of crash. So, all right, so you can see that I've gotten 65 exceptions, and it says this is 3 faults. And if I look at this, you could see I got that same thing I got before with that JSON5 thing. But then I have these 2 new ones about something about the property, text being null. And you could actually see that they're happening on 2 different lines. So this one's on 234, and this one's happening on 271. So I want to show you 2 things related to that. So one is just that step of what does it mean to be a fault. So essentially what we're doing here is we're saying that every time we caught a exception, we put it into this list. But then what we do is we process each of those lists, each of those exceptions, and we split the stack trace, and then we look at that kind of @ line, which is this one right here, and we just hash that. So we're just saying, like, if we haven't seen this one yet, add it to this list of reduced things. And that's essentially what ends up getting printed out. So only unique stack trace lines on the top level are collected. And if you see the same exception again, then we don't bother reporting that again. And so that way, if you're actually going to show this to a user, then they would get only the things that they care about. So these are actually 3 legitimate crashes, and there's actual input that you can use to recreate that. So that's pretty cool. Let's look at what it would actually mean to get this. So imagine I got this as a report saying that there was a crash here. Well, then what I can do is I could go at least to this code itself, which is the code that we're testing, and it says process tokens in line 271. So go do. All right, and it's saying can't set text of something null. All right, so it looks like something happened to cause this parent token to be null, right? And if I were to look at the input file, which you can see they're all here, well, lots of them there. It's gonna be slow. I could open that up and actually look at what might be causing that. And I think in this case, what happened is remember the original markdown format, if you try to give a property for a question where it didn't have a question header, then the parent token is null. So this is a flaw in the logic of the code, and that's something that could be fixed now, right? So we would know all about this. And what's cool about this is we can automate all this without knowing anything about the code, and we can even integrate it into our pipeline. So we could have a new stage in our pipeline testing where we basically did fuzz testing on a program that we built. So if our program is something that receives actual input and you can actually run on a command line, or it produces some sort of binary that you can run, then this is actually perfect for doing fuzz testing. If the program isn't really something that's going to be runnable with a single input, but it's maybe more of like a web server, you can actually still use the fuzzing technique, but just targeting on specific programs. And so a good example of this is, imagine you had a Java program and you provided a fuzz annotation to a function. Then what you could do is you could have a tool that would look through all the code that says, I want to be fuzzed. And then what that tool would do in the pipeline, it would just randomly generate inputs for those functions to see if there's any problems. And so we actually have a tool that just like this, that one undergrad student that worked with me at one point, and he basically built a really cool tool that works with Java and Maven. You just have it as a simple plugin, and all you do is you just say, I want this thing to be fuzz tested, and it will actually generate random test data for classes and strings and all sorts of stuff. And I don't know, pretty cool. And so that you could do a lot with this. And he ended up integrating this into SAS. So they actually use this in SAS to run all their tests. Another thing that's actually pretty neat is this idea of minification. So if I were to pick one of these and okay, let's jump to 711. All right, so there was something here. Oh, I think this is what caused that question to be invalid, because I randomly inserted stuff here. But say if this was much longer, say like this one, and I wanted to see what was causing the the bug and I wanted it to be much shorter like this, you can actually use minification on the input to automatically delete some of the input, random parts of it, and then try to see if you could still regenerate the crash. And this technique is actually really popular for automated testing, of where you can use this to get the minimum possible input that will still replicate the bug. And they use this a lot in, say, compiler testing, of where they try to generate random, say C files for a C compiler. And then when they find a crash, then they will run a reduction step to see if they can automatically make a tiny little C program that they could then give to the compiler author to say, look, this is causing a bug. And so there's actually a really nice tool for this called C reduce that will actually work with pretty much anything. It doesn't just need to be C. It could be anything that has a text input and has some sort of oracle of saying this was good or bad, then you can run this. And so you could run that with just a real simple bash script. So it just looks something like this. C reduce, a test file that says how to run it, and then the file that you're reducing. So in this case, this could just be the markdown file that we're running. All right, so there's one more thing that I'd like you to do, which is these two experiments. So one is that I'd like you to try this idea of what happens if you insert a array reverse in front of all your code. And I want you to do a little thought experiment before you do it, to think of, do you think that would actually help you find more faults or less, right? And think about why that is the case. And then the second step I'd like you to do is to increase the number of tests that you, iterations that you run. And the way that you can do that is just by adding a new parameter when you run node index. And so that would just mean that you're running fuzzing for longer and more, right? So I want you to try a couple numbers that you can do 15K, 100K if you want, and just to see, did you find anything new? Does that change? Do you think this helps reveal more faults or not? Is there a point of diminishing returns? What's that look like? And what drives that? So I'd like you to try that too, to wrap up. And then I'm going to leave you with a real brief conclusion, because I mentioned early on that fuzzing was related to mutation testing. And I like to say that they're basically the same thing, except that you kind of change the premise and the targets of what you do. So rather than randomly mutate the inputs for a program, we kind of reverse it. We simply mutate the program itself, and then we check to see if our test suite that exists will say that that was a good or bad program. Because the idea is that if the program is perfect and any change to it, such as like flipping, a less than to a greater than symbol, should be a flaw, right? That should not be a good program. And we would want our test suite to be able to catch that, right? And so the idea for mutation testing is you could generate, 1,000 mutants like we did, but instead of that being on input, we do that on the program, and we create 1,000 versions of the program that differ from that golden version of the program that's right. And then we check to see how often can our test suite kill or eliminate and identify that those are buggy versions of it. And essentially mutation testing coverage is essentially saying, of X mutants, how many can you cover, right? How many did you identify? And we will be able to have a chance for doing that by, instead of randomly mutating inputs, we're going to do this on code. And that's going to be something that we'll do in our second milestone. So that will be fun. All right, but that's it for the workshop.